It's 8 a.m. California time, and good morning to our friends in Americas, and good afternoon to tinyML enthusiasts in Europe, and good evening to our folks in the Far East. Welcome to the tinyML Talk series. My name is Evgeny Gusev. I am from Qualcomm AI Research, and I'm also chairman of the board of the tinyML Foundation. And today we are going to talk about tinyML application for industrial IoT, and that's one of very promising applications of tinyML. So as tinyML community grows, we see more projects of this nature, we see more collaborations, we see more partnerships. And this talk today is actually a reflection of such a partnership between two known companies in this space. It is my pleasure to have two distinguished speakers today. It is Chris Rogers, the CEO of SensiML Corporation, and Theo Kersjes, product manager from onsemi, and both of them are presenting from Oregon today. And the title of their presentation will be the value of Edge AI for industrial applications, onsemi and SensiML industrial IoT solution. So before we start, let me acknowledge tinyML strategic partners and sponsors. It's AUN Devices, ARM, DeepLight, HMPulse, EMSA, GreenWave Technologies, Gravity, HOTG, Imagimob, Latent AI, Maxim Integrated, which is a part of Analog Devices now, Kixo, Qualcomm, Reality AI, Renaissance, Ericsson Technology, SAP, Seed Studio, SensiML, Stream Analyze, ST Microelectronics, SynSense, and Sentient. And if you're interested in joining this distinguished list of companies, you can contact Olga at tinyml.org or sponsorships at tinyml.org. One big announcement here is our flagship event is coming in about 4 months. tinyML Summit 2022 will take place in the end of March, and it will be an in-person event. We are very excited to host an in-person event. It will be in the San Francisco area. Registration will open in about a week time frame, and there is still some time to submit posters if you're interested in presenting there. Also, just like this year, next year summit will have the best product of the year and best innovation of the year awards, and nominations are open until February 28th. So you can go to the website, tinyml.org, and you can find all this information there. And in conjunction with the summit, we will have the second tinyML research symposium focusing on the academic research in this space. It will also take place on March 28th, and deadline for paper submission is December 17th. tinyML Foundation conducts many different events and many different activities, and one of them, which we have a special focus and a special passion for, is tinyML for Good. 2 weeks ago, we had our first tinyML for Good workshop focusing on these 3 areas: healthcare, STEM, and conservation and sustainability. So all the information from the website and the videos are available on the tinyML YouTube channel. And if you're interested in joining, you can contact email forgood@tinyml.org. Our next tinyML talk will take place next Tuesday as usual. The presenter will be Mark Musenberg from Harvard University, and he will be talking about multilingual spoken word corpus and massive keywords supporting data set. That's going to be very interesting for those interested in the audio applications of tinyML. And at this point, let me introduce our distinguished speakers, starting with Chris Rogers. Chris Rogers is a industry veteran. He has over 25 years of experience running embedded systems, wireless communications, and algorithm development. Chris has led several high-profile teams in companies ranging from Intel to startups. Chris focuses on building and supporting teams capable of bringing cutting-edge technologies to production, to reality, delivering results and customer value quickly. Prior to spinning out SensiML from Intel, Chris was general manager of Intel's machine learning software tool business and held prior positions and product line manager, turning around Intel's almost like $1 billion business in Wi-Fi and Bluetooth modules. Chris is an engineer in his heart, and he started his career in automotive test measurement as both developer and end user for IoT systems. So it's kind of a long history of Chris doing IoT, starting from IoT and doing IoT now with a lot of machine learning capabilities now. And he holds a bachelor degree in mechanical engineering and an MBA from Carnegie Mellon School of Business. Thank you, Chris, for joining us today. And Chris's partner will be Theo Kersjes. Theo he manages a team of product designer and application engineers for power and sensing solutions. He also has a long history of industrial accomplishments working for different companies. He started at Philips NXP, focusing on digital video processing, and moved from the Netherlands to the Bay Area to work on broadband routers, VoIP, and cable modem system. And then he worked in the RF area, where he gained diverse experience developing product for hearing aid applications and Wi-Fi modules. And then he was in the NXP application group, where he managed a team working on digital power, point of load, Wi-Fi, and Zigbee applications. He joined a startup that developed a 60 gig wireless connectivity. And today he works for onsemi. He has patents, and also he is a known public speaker. So again, we are very fortunate to have two industry veterans sharing their wisdom today on using tinyML for industrial IoT applications. Okay, Theo, the stage is yours.
Welcome, everybody. Today we're going to go over these 4 topics. This is the agenda for this webinar. First, we're going to have a quick look at the use cases in a wider format for Edge AI, then focus into industrial sector. We're going to have a discussion about why Edge AI, and then go deep into the workflow for SensiML. And you see on the side in the picture there as well the hardware that we're using for this specific use case from onsemi. And then lastly, we have a video where we show how it's all coming together and how it's done. So the result of this will be a robotic application that detects some of the movement of the robots. You see here in the picture 2 robots. We have a Adreno, the orange one that has a sensor node on it, as well as the universal robot behind it that's more of a professional industrial robot that has the same sensor node on it. What these sensors could learn in this scenario is, for instance, which of the motors is used most in certain industrial production applications, and you could then target maintenance on those joints or on those specific things in the robot. We have some other examples we're going to go through with this in a little bit, so let's get started. First, some key use cases. I wanted to point out that onsemi is a leader in image sensors. I know we're not going to talk about image sensors, but more about another compute paradigm where you lower compute for the algorithms to sense, for instance, movement, etc. But we see in this space where we're leading, and what in the history of the years in past where we had a lot of algorithmic work, that this happened, And I wanted to point that out. What we do here, for instance, is looking at image sensors to combine them with IR in the same sensor. So we have applications and products that can do vision as well as depth with LiDAR. So you can have security cameras that detect facial recognition, but also depth of the face, or how far it's away from the camera and other characteristics. So there's a lot of work being done in filters in these image sensors, as well as having other light or IR sensing capabilities. So we then come to some of the applications that historically these image sensors are used for. It's just exploding. It's all over the map. There's a lot of, the top right, industrial applications where very high resolution sensors are used to look, for instance, at screens of products that are created. It could be tablets or phones, and to detect if bits are not correct, but also more and more in AI scenarios where you have inventory control or tracking of products around certain production lines. In the bottom right, I wanted to point out our automotive product line. We are the leaders in automotive imaging. And there, of course, there's a lot of stuff going on with automating car safety features and even up to autonomous driving. And I wanted to point this specific application out because most of you are drivers or have driven a car or sit next to somebody, and you can feel that if something changes in the car very quickly in your car, if you drive it every day, and you will notice that something is off. And this is kind of an example of an expert that you are in that application that can detect quickly if something is off. And that's the expertise we need to find in industrial applications for different equipment to sense that as well. And sensors can do that even quicker. So that's a good example of a anomaly detector. For instance, if you implement that, if something is off, it will signal that, and then action can be taken. With that, I'm going to give it over to Chris to give us some more examples in industrial setting.
Thank you, Theo. So as we consider the types of use cases that we would find in industrial settings, I think most people are very familiar with AI from the standpoint of image and video recognition and looking for objects. But in the industrial world, as in many different sectors, you have sort of the mass of the iceberg that lives below the water, which is all the sensor types that fall in sort of the time domain realm. So as opposed to spatial data, which image and video and AI for recognizing objects within video. We also have as many applications, and this is sort of the realm of tinyML, is to take those time series sensors and perform pattern recognition on the types of rich dynamics signals that you get from those. So as we think of the kinds of time series sensors we see in industrial, these can include things like audio data. It could be motion or vibration is very commonly used, but the list goes on, right? So you've got pressure, you've got strain gauges and load cells, and just many different sensors. In fact, there are billions of sensors out there that can provide valuable context as to what's occurring within the factory setting. And so the focus of SensiML's tools is to provide AI and tinyML at the edge for those types of sensors that are time series based, which extends beyond just industrial applications. We actually got our start from the Intel days in the consumer realm, looking at wearable devices for things like smart virtual coaching and whatnot. But whether that's consumer or automotive or healthcare oriented devices, agriculture, the kinds of use cases that you can make valuable insights from these time series sensors is quite extensive. And then as we specifically drill into industrial, the kinds of things that are possible are predictive maintenance, where I'm using maybe vibration sensors or accelerometers located at strategic locations on particular machinery, combined with audio data to give me sort of auditory context of what's happening, the same way that a machine operator can hear if there's an issue with the machine. Anomaly detection is a simplified version of that use case, because very often it's challenging to come up with all the fault states. If I've got a plastic injection molding machine, I may not have the practical ability to simulate all the different faults that I'm interested in understanding. So sort of the simplified case that we commonly see in industrial for these types of use cases is to characterize normal machine operating behavior. And then if you see behavior that falls outside of that, sort of norm, then you can flag the event. And over time, as you have maintenance personnel that root cause whatever the underlying condition was that caused the fault, then you can label those so that in subsequent instances when that same failure occurs, you can avoid sort of the forensics of figuring out what it was, because the machine will now recognize those particular patterns. And so over time, you gain that expertise and you gain the insight and build increasing intelligence into those models. But beyond just looking for things that go wrong, it's also sort of characterizing things that go right and making sure that things stay right. So process control and inspection, machine monitoring. The application we'll show here for the robotic arm example is to put a device on the arm and look for a variety of things, not just anomaly detection, but also just to characterize how many cycles has the machine gone through, what state is it currently in. And this kind of information it can be gained either through the system itself with some integration challenges, or if you think about these as add-on sensors, then they can be readily adapted to a variety of different processes and machines within the factory environment, so to give you sort of a common approach for understanding what's happening. The final use case in industrial that I'll highlight is that when we combine sort of the wearable use case with an industrial environment, we have unique opportunities to do things like gesture and motion control for smart glasses or augmented reality devices for machine operators and maintenance technicians within the factory, or even for characterizing motion of humans working in close proximity to automation to ensure either compliance or to ensure safety, so that any events that might have a safety impact are noted quickly and acted upon. So as I mentioned, for this particular example, we're going to highlight one particular demo use case that onsemi and SensiML have developed for this robotic arm to highlight what's possible when you take a low-cost, low-power, multi-sensor device that has wireless connectivity and apply it readily to an existing piece of equipment as a retrofit. So as opposed to having to have operators and industrial engineers on the factory floor dig into what is already existing code for the automation within the facility, which they're kind of reticent to do, because once those systems are functioning and right, any changes to that code requires further test and validation, not to mention the time that's involved where those systems are offline to be modified. So our ideal sensor for a factory would be something that you could literally just Velcro to a piece of equipment. I use Velcro loosely, right? But the concept is that I can take a device and I can affix it to a piece of machinery to characterize the movement without having to make any modifications to the underlying control logic. And so that's what we'll show here for the robotic arm. And the same process could be used so that you have a common platform that can monitor robotic arm or a conveyor belt or the plastic injection molding machine or an extruder or pumps and valves or other critical points within the factory environment using a standardized approach that doesn't interfere with the normal operations. And then from that, you can characterize the motions to understand things like, is the robot arm having some kind of an interference issue, where some kind of unexpected tooling, or the product isn't positioned correctly, or there's some type of fault, or just simply characterizing where is the robot in its current state. So if you're building up a sort of a factory-wide view of what's happening and using common elements as opposed to having to do integration of lots of different dissimilar systems, there's a lot of appeal to having something that can be very basic and applied readily to give you that sort of full factory view. And we've done this using the RSL10 device, which as the sensor node, you can see in the picture here where it's fixed to this industrial robotic arm here. So how do you build such a system? That's where the SensiML tool comes in, which is to provide a platform for users to be able to collect data so that they can readily build models, and then those models can then be applied to do pattern recognition and look for the events of interest. We'll get into in a subsequent slide sort of the benefits of edge versus cloud, but being able to provide that AI right at the point where it occurs and not having to do so in the cloud simplifies the process greatly in terms of not having to have distributed applications for processing. The tool also provides you with sort of production grade models with the transparency and traceability that you need so that you can have confidence in the models that you build aren't just this black box and not understand really either how they function or if they're functioning as you would expect. The process also is one which uses a technology called AutoML. And I like to think of AutoML as using machine learning to build machine learning. So there's a little recursion there, which is that big stumbling point for many implementers of AI or machine learning is that it requires a fair bit of expertise in order to understand how to even get going, right? The mathematics get deep pretty quickly. The intuition about which feature extractors provide you with the best input vector, and then how to configure the hyperparameters for the model, or even which model to choose, are fairly complex decisions typically done by a data scientist. And since data scientists don't grow on trees, many teams don't have access to data science expertise, but they certainly do have domain expertise within the application they're trying to build. So if they can characterize the things that they're trying to understand, what AutoML can do for you is to take a labeled data set that a domain expert could readily generate and do the data science work to translate that into functioning code. At the same time, I don't want to characterize this as a point and click process where I'm just giving labeled data and I'm sort of click the button and pray that the model I get is going to be one that's satisfactory. The toolkit allows you to do sort of the simplified approach where you put basically the process in the hands of the model generation engine to come up with what it believes the best model could be. But then at that point, it can be very interactive where you can drill into the model, make changes at will, redefine which classifier types are used, and tune the model as necessary. So I think the combination of simple to use, but also powerful enough allows you to not outgrow the model as you gain expertise or as you bring on data scientists who are capable of working at that level as well. And then finally, I think I mentioned the notion, particularly for anomaly detection, where a lot of times it's not practical to fully characterize all the fault conditions. So the ability to do edge learning and to have continuously refined algorithms that learn as certain edge cases arise is an important aspect of this too, and we support that capability. So with that, then I'll quickly touch on some of the differences between cloud versus edge, and why that matters, and then we'll get into the workflow and then proceed with the demo case. So for those who've been with the tinyML group, I think a lot of this will be kind of common knowledge. But for those newer to sort of the use of AI at the edge, some important points of why that's interesting, right? So if you look at the way IoT was several years back, we had embedded devices that had sensors. You might affix those sensors to devices. And the notion of collecting data for Industry 4.0 and cloud-based BI dashboards is and still largely is a process of taking rudimentary sensors like threshold limits, right? Like is this temperature in or out of spec, or has this light sensor been triggered because a product went by on a conveyor belt? Basically, like binary inputs. And have those trigger events that get sent back to a cloud. And the cloud dashboard can give you that sort of high level, but fairly basic view of simplified sensors. If you tried to accomplish that same thing using very dynamic time series sensors, this is what cloud-based centralized data analytics would involve. So here I might have microphone sensors, or I might have high sample rate vibration or motion sensors. And I'm just using the device as basically a dumb data collector that's digitizing the information, doing the A to D, and sending that to the network. The problem with that approach is you think about a typical factory, you might have thousands or tens of thousands of points within the factory that you wish to monitor. And if each one of those is generating data that's sampled at hundreds to kilohertz, you quickly see where you have network congestion and bandwidth problem. Any individual point could be generating 100 kilobits per second or more per channel of input. And then multiply that times the number of devices in the factory, and you've got a fairly congested network that's just sending raw data. If those devices need to be wireless, because network drops typically are about $1,000 each in order to get work orders to have strung with good old RS-485 or whatnot. I think we're seeing more use of wireless sensors, but those wireless sensors are typically battery powered. So if that battery needs to operate the transmitter on the radio, that's a much larger power consumption than even the processing on that particular device. So the impact of just streaming continuous data wirelessly will quickly impact your battery life with a higher power consumption. You've got data security issues and for privacy. So if I'm taking audio data, for instance, that's fairly sensitive, as well as sort of proprietary factory processes where I don't want that necessarily to be sent over the network. And then what happens if the network goes down, right? If I have a network outage, then do all these, the sensors that I'm using for monitoring become effectively useless for giving me insights as to what's happening? So these are all sort of the challenges of having a centralized approach for data analytics, where all the actual insight is being generated remotely in the data center and in the cloud. The final one here is that if I have to take the data and send it to the cloud and then react locally, I've got round trip latency involved in doing that as a remote analysis. So then you compare that to doing edge AI, as the tinyML group is sort of focused on. Right? We take the AI, we integrate that as firmware within the microcontroller that's running the endpoint device and doing the data collection right at the source where the physical sensor is. In this case, because we can do the pattern recognition, I might be looking at something very complex, like a vibration signal at kilohertz in multiple axes, and looking for a very specific type of vibration to trigger an event that says that I've got an imbalance or I've got a faulty coupler on a machine motor shaft. And if I can determine that locally within the microcontroller, then the only thing I really need to do is signal that I've got a problem. And that can be done within bits. right? So the network traffic isn't a continuous, logging of just constant data, 99.9% of which is just not interesting, right? It's the same old data, everything's good. But instead, I'm conveying only events of interest. And so the impact on the network traffic can be vastly less. And then consequently, if that's a wireless device, I'm only turning the radio on if I have something interesting to convey. So I can have much longer battery life. And you might think that the AI that's taking place would offset that. And certainly it does, but we're talking actually an order of magnitude or less in terms of what it takes with a modern processor to do the classification locally versus the physics of RF transmission and the power required to convey that wirelessly. And so the sensor data stays local, so you're not conveying that sensitive data over the network. And if the network were to fail, or if you had an outage, for instance, you still have the local intelligence of what's going on. So if you need critical machine response, like I need to turn a line off, or I need to engage a solenoid to prevent something from causing more catastrophic effects, I have the capability of doing that because I'm doing the intelligence locally at the device. And then because you're not relying on the network, that round trip latency that we talked about really doesn't factor because you've done that all locally within the processor. So there are a lot of advantages here where you're using the cloud to aggregate data. I think the cloud has certainly its use in the aggregation of the thousands of data points and the big picture view of what's going on in the factory and looking at the broader data analytics. But there's no need to have the cloud doing the individual pattern recognition to make sense of the raw sensor data within the controlled domain of that particular endpoint. So with that, then I'll touch on, so what's the build process for accomplishing this? I like to break it down to there's three phases here, right? What we're doing here is categorically known as supervised machine learning, which is that you're taking data sets and you're applying known ground truth to them, right? So I could be looking at a piece of machinery and using vibration data, for instance, and what I want to understand is this particular pattern that I'm seeing from the sensor, what does that represent? Is that normal operating conditions? Is that some type of a fault condition? And if so, can I characterize what that fault is and label it? That process of data labeling can be quite tedious, and it can also be very challenging to do because this is sort of the intersection between the digital world and the physical world, where I have equipment that I'm monitoring and I'm trying to capture realistic sensor data and then label that. So there are a variety of different approaches, but I think the important piece is that you need tools that help aid that process, because if you don't do that well, then it doesn't matter how effective your machine learning model might be, or if you're using a cutting edge classifier, if it's garbage in, it's still going to be garbage model out. So your accuracy will be poor because the model can only train to the fidelity of the labeling that took place when you collected the data initially. So we put a lot of effort into a tool we call Data Capture Lab, which is kind of, you think of it as like a ML ops tool for helping automate a lot of the process of collecting the data in the first place and treating it with the same rigor that a coding, like a programmer would do for version management for their code, right? So we've gotten more sophisticated in how we write code from a programming standpoint. We also need to get more sophisticated about how we manage these data sets so that they become true assets and we can understand and manage them appropriately. So we have version control. We have the ability to have multiple users that are collaborating. You might have test technicians whose job is solely to capture the data, where you have people offline who are the domain experts who can go back and analyze that data and provide the labeling. That kind of a workflow supported with this tool, as well as just the scale of having multiple people performing that task and doing session management and version control, so that if somebody were to do it incorrectly, you can extract that data out. It's all database driven, so you have a fairly rigorous process to ensure that you're getting high quality labeled data coming into the process. And then the second phase here is this, AutoML piece, which is, once I have a quality labeled data set, how can I build the model without having to involve, months worth of effort from a data scientist who's, hand tuning these models. And so the AutoML, can very rapidly use cloud computing power to traverse the data sets that you have, look at, over 100 different feature extractors, different segmentation approaches, different classifiers, ranging from neural networks down to very, the sort of classical ML, decision tree models, distance-based classifiers, support vector machines. And the best model is the one that's accurate and small enough to fit within the device that you want to use. So, the goal of this phase is really to automate the process of coming up with the most efficient model that's optimized for the target parameters that you're seeking in terms of either accuracy or selectivity or sensitivity of your model. And then finally, we have the important case of I need to test that model, and we have a tool called Test App that allows you to do that on device. We also have an emulation tool that allows you to do bit exact analysis of data that you've set aside purely for test purposes and not used during training, and can do that all sort of in the SensiML environment without having to physically flash a device. But I think the proof is in the pudding. Oftentimes where I want to flash the device, I want to put it in the field and test it, and so the test app gives you a way to empirically test your device and ensure that the behavior you're seeing is the one you expected based on the emulated results. So with that, let me turn it back to Theo, who will describe more of the hardware side of the solution.
Thank you, Chris. So for data capture and test and deployment, we are using the device that is shown here in the bottom right, the industrial ultra-low power sensor kit. This uses an RSL10, which is a Bluetooth device, a SoC with a microcontroller on board. We'll look at that a little bit in depth in the next slide. But I wanted to highlight here a couple of more platforms that we have for these type of applications. To the left of the industrial node in the bottom right, you see a smart shot camera. This is again a system around the RSL10, so a Bluetooth operated node, but it does collect image data. And it could be used in smart retail to look at the opposite aisle to do inventory management, or take pictures once or twice a day like that, or in growing plants or other things where you have a relatively low sensor input, maybe 5-6 times a day, and you do some of your AI work on that. It's definitely not intended for video because that is the bandwidth for the Bluetooth link would also not allow to do that, and it makes it less efficient. But there's these use cases where you want to look at something over time, where this is very applicable. Both of these are battery operated. Then we have to the left of that again a solar power sensor platform. Again, same RSL10 with a microcontroller that now has different sensors, but it completely runs off a solar cell. So that can be used where you cannot access it to change batteries once a year or in longer times for some of these applications. And then even to in the bottom left, we have a platform that uses mechanical switch or mechanical movement to generate the power. So there's no batteries in this device to then boot up the RSL10 and have it send its Bluetooth packages for some kind of sensor data that you want to monitor. And this can be used for light switches, where you see this, but it could also be on, for instance, a fire extinguisher. You pull off its mounting bracket, or other applications like that. Top left, then there is the development platform that goes with the RSL10. And that exposes the pins of the device, so you can hook up your own sensors and your own hardware with that and directly develop on that platform as well. In this use case, we use a board for the development platform to receive the Bluetooth sensor data we get from these nodes, and that's linked to a PC and then connects into the SensiML toolkit. And then in the bottom left, we use bottom right, we use the sensor node to collect the data from the robot or any device to analyze it. I'm trying to get to the next slide. Chris, if you could help me, it seems to have an issue again.
Yeah.
I guess it's not.
Yeah, I think we're fighting for the mouse here or something.
Or you can just do next slide if you can do it. Maybe we did. Is this one slide? There we go. So you see thank you. Here you see the block diagram of the RSL10. I just wanted to point quickly out to the blue parts on this system. So there is an ARM Cortex M3 on here, maximum running at 48 megahertz. So quite some CPU power is available. There is a DSP. In our case, this is used for some audio codecs that we have for that in this platform that fully supported. It's not used at this point for the Edge AI applications. There could, of course, be a lot of opportunities there. And then you see the baseband radio, which is a Bluetooth 5.0 radio for this device. To the left is a block with a memory requirement, so that's important. You can see we have 384 kilobyte of flash for applications to be stored and used. If we go to the next slide. So here's the sensor node itself that we created as a reference design for these type of sense applications. It has multiple sensors. In the bottom right, a Bosch sensor for 3-axis acceleration, navigation, gyroscope. Bottom right, then the humidity, air pressure, air quality, and temperature. And there's a microphone on this system as well. In this particular demo, we're using the acceleration and gyroscope sensors from this platform. We go next. And for us, a really important aspect is the power, power consumption. We say we're lowest power of ultra low power systems for Bluetooth transmission, as well as the CPU benchmark still have a good performance on the CPU, particularly for Edge AI applications. That's an important factor. I'm showing here the RSL15, which is a Bluetooth 5.2 product that we launched last month, and I compare to some of the other competitors in this space, and you see, for instance, for the power usage in standby mode, that the RSL15 and RSL10 are the two leaders in this space. The RSL15 does not have a DSP on board. It has a different ARM core, an M33, which is a security core. There's some more security features around that product. So these are the two products we have and platforms we develop around those IoT edge applications that can be used to do some compute locally for these solutions. If we go to the next slide. And then lastly, we have a community forum for the RSL10 and RSL15 there, where you can share expertise and answer questions that other customers have, or start your own track of questions. And this is very helpful. There's firmware, there's solutions, there's many, many different applications, people focusing on audio, people focusing on other types of solutions with these two products. So with that, I'll let Chris lead us for the video.
Okay. So in this piece, then we'll get into the demo itself. As we described, the test setup here is that we've got, in this case, we're using a basic Arduino robotic arm as a sort of a proxy for the commercial or industrial robot, but the concepts are similar. There's a multi-degree of freedom arm, and we have the RSL10 that's connected to the device, and it's wirelessly transmitting. Initially, it's sending the raw data so that we can capture and label the data. Then we'll show how the model is built, and then the classification is then done entirely local within the RSL10. So in the video, we'll start with sort of the end result, which is the autonomous model that can run entirely within the RSL10, taking the motion data that it's capturing and then classifying that based on the defined movements, and then a bit on the process, so you see sort of what the software looks like for building that. So with that, I'll just launch the video and we can view this.
This demo shows how sensor analytics using Edge AI running on autonomous sensor nodes can provide real-time insight and event notification for critical factory processes. This insight can be achieved using ultra-low power sensors, like onsemi's RSL10 platform, combined with auto-generated AI code created with SensiML Analytics Toolkit, running directly on the sensor node. To illustrate this, we show how raw motion sensing data can be transformed to give real-time feedback into the performance of a robotic arm. We can detect both key movement states and any anomalous behaviors deviating from programmed movements. By utilizing sensor nodes that operate independently from the robot arm's control logic, we need not modify and re-verify the existing programming. The sensors are essentially add-on devices that monitor and report separately from the target machinery they are sensing. What you see presently are motion classification outputs from the Edge AI robotic arm application model. The classifier is configured to detect targets or positions, and paths or the transition sequences of move instructions to reach successive targets. Additionally, the classifier includes an anomaly detection class labeled as OOPS to indicate unknown or unexpected motion within the program. Such movement might indicate collisions with other equipment, the workpiece or manufactured work-in-progress goods, or human workers in the proximity of the robot. Creating the Edge AI model is accomplished entirely within the SensiML tool suite, and starts with Data Capture Lab to collect and label training data used to teach the model's behavior. With training data in hand, SensiML's Analytics Studio automates the data science tasks, using AutoML to generate optimized embedded code for the RSL10 device. Using a straightforward visual interface, Analytics Studio allows the developer to quickly define and tune models based on queries of the overall dataset, key model parameters, and hard constraints like available model memory footprint. Unlike less powerful Edge AI tools, SensiML provides the developer with full control with the ability to expand or restrict the AutoML search, isolate feature classes for use, and choose classifiers from classic ML to neural networks to deliver production-worthy code. Resulting SensiML models can be explored in detail with graphical visualization and full transparency into the model pipeline. Model validation is automated with bit-exact emulation of target device behavior before ever having to flash a byte to hardware. The final step in the process is generating the SensiML knowledge pack, or embedded model code, for the RSL10 hardware. Using add-on sensor nodes as retrofits for process monitoring of existing equipment brings powerful new capabilities and flexibility for production optimization, safety compliance, and predictive maintenance. To learn more about the Edge AI solution powered by onsemi and SensiML, visit sensiml.com/partners/onsemi.
Okay, so with that, Theo, you want to highlight a couple of points here before we get into the Q&A?
I think this is self-explanatory. Let's get into the Q&A.
Great, okay.
Well, thank you, Theo and Chris, for sharing this interesting use case with the global tinyML audience. There are several questions to entertain. One is, at the beginning of your presentation, you showed a variety of different use cases, both from the SensiML perspective and also from the onsemi perspective. So what are the areas where you see most traction with customers today, and kind of where do you see most growth in those areas in the future? I mean, you show several examples. Are there any particular kind of industries, use cases where you see most?
We're seeing a lot of interest in predictive maintenance and anomaly detection currently for sort of characterizing machine faults. So I'd say a lot of the use cases that are currently in the process are those, right?
Yeah, from our side, I just wanted to point the imaging sensors that we have and that technology as something that's ongoing and it's still happening. There you see mostly something partitioning going as well. If you have very high resolution image sensors, you don't want to send all that data. So do you do at the edge object detection and only send object lists over? How that then impacts your decisions. If you have self-driving cars and you only have objects, you cannot distinguish between adults and children, if that would need to be a distinction you need to make. So there's many discussions and around doing it at the edge or sending the data at low latency to the cloud. That's another thing that's of interest, where you see applications happening that cars that share their video would map a certain area in the city, and you could have an AI in the cloud detect where your potholes are in the street and have some kind of a service to the city to give a list where they need to repair the road versus the autonomous driving aspect that needs low latency. So that's what you see in image. And together, in industry, we see, of course, now the focus on other data than image sensors, which is very interesting and I guess a leading edge field.
Yeah, great. Well, thank you. Now, a question to Chris. Definitely, AutoML tools are becoming more powerful and more useful in this community. What makes SensiML AutoML tool differentiated and unique compared to what other people use? Are there any special features, special things that people should use SensiML over other AutoML tools available on the marketplace today?
Well, I guess there's two things that come to mind. One is that from the ML ops standpoint, we put a lot of development and investment into the tools for just the front end piece for data collection and curating the data set in the first place. Where we've seen a lot of the issues, frankly, when customers come to us to say, hey, we have an existing data set, we'd like to leverage this, is that when that data set was collected, they did it so prior to having an AI inferencing approach in mind. And so very often we find that the data isn't sufficient for what's needed. And so there are really some practical challenges in terms of how do you collect data well in the first place. So that's where the data capture lab is something we have unique that ensures that the front end of the process is giving you good data coming in. The other piece is that I think there's been lots of attention and focus sort of on the frontier of models for using neural nets, but the space isn't new, and even neural nets themselves have been around for decades. But the overall, a superset of classifiers includes some very basic approaches like decision tree models and distance-based classification, k-nearest neighbor, a lot of these other approaches. So in many cases, we find that the best answer isn't always a neural network, right? So if you're trying to target a very resource-constrained device that doesn't have a lot of RAM or MIPS available, or you're utilizing that for some of the user code as well, trying to fit the inference model within the envelope is something that we focus on by having a search process that doesn't just factor neural nets, but also looks at feature engineering on the front end and with simpler models that can give equivalent results.
Well, thank you, Chris. I definitely agree with both of these comments on the classical classifiers and in the data collection. And talking about data collection, could you quantify, like in this particular case, the robot arm training, how much data do you need to collect to really develop a good model there, kind of ballpark, either kind of in terms of time or in terms of number of
sure.
Ballpark, I assume it varies from case to case, but kind of just to give the audience an idea, like for this predictive maintenance type of operations, for production type of deployment, is it like worth of a year type of data, like what Tesla is collecting, or it's like 10 minutes in a lab type of thing? Kind of give the scale.
The very unsatisfactory answer, but realistic one, is that it depends, right? It depends on the sources of variance that you have, and how many other factors sort of play into it. It's like a design of experiments, right? If for the robotic arm example, because robotic movements, if they're acting normally, they're very predictable. You can get sort of a baseline characterization with a very few. For this demo, I think we did about a dozen collections per each of those movement patterns that you see. So it's not that you need months worth of data in order to converge on an answer, which is a lot of what people criticize neural networks with back propagation is that you need lots of training data in order to converge. But it just the nature of the problems really sort of defines the process. And so because you don't always know upfront how much data is truly going to be needed, we typically advise our customers to go through an iterative process where you pick, say, 10 to 20 examples, run it through the workflow, and then you can see what your distribution looks like, and you'll have a better sense then, without having invested an inordinate amount of time on data collection, to know the size of the problem you have. And then so from there, you can come up with an approach for how do I scale this up to what I need.
Great. Well, thank you, Chris. Now there is a question for Theo. RSL 10 is a very interesting platform, and it shows a variety of different ones, kind of for different applications. There are several questions. You mentioned that it's a battery operated. I assume it's like a coil cell type of battery. That's what
coin cell, yeah, 2023 for the industrial sensor node. The SnapCam, the image sensor one, has a slightly bigger coin cell battery. But yes, coin cell.
So what is power consumption for this? Obviously, I mean, you mentioned some different regimes, like when the whole platform is in the sleep mode and then you wake it up. But so like, what is the average power consumption? You're talking about microwatts?
It's standby mode is nanowatts, and on receiver standby mode is in the milliwatts. I can give definitely the specific numbers. But that's where we're thinking. So if the whole thing is in sleep mode, including the Bluetooth, it's nanowatts.
And when the M3 is up, how much the power when the M3
it really depends on the profile. I have the link here in the slide. You can see the EMC benchmark link. People can go there and find the part, and you can get there the core benchmarks for the CPU full running. all the numbers as I showed them on the slide. Yeah.
Great. And then if developers are going to try this board, what kind of software environment, what kind of software tools can they use to develop the applications on the RSL10?
Yep, there's a full software environment. There's Eclipse-based onsemi environment where we have all the software applications for available. On that slide, we just went away off there on the website. You can see a table with all the different software applications you can load. There's example code for a free OS to run on them. And the code for, of course, operating the Bluetooth and all the interfaces of the device. And then for each of the different platforms, we have source code as well, including now the source code for this specific application. So if you want to reproduce this webinar, you can go to the website and download the code for these two boards, the receiver board and the sender board. Order those and connect it to your own device to do data capture.
And assume the board is available now, and if people want to buy it, like how much would it cost?
It's available in DigiKey for the sensor nodes. There's two versions. One comes with a JTAG solution. I think that's around $75–80, and there's a half that price without the JTAG, something like that.
Okay, sounds good. And then there is a question for both of you, I guess, because you are industry veterans in this space. There is a question from Naresh. What about security issues once we deploy in Edge? What protocols are using and so on? Can you comment? I think you touched upon this a little bit, Theo, in your presentation, but can you elaborate a bit on the security?
I can start, Chris, if you want. So on the hardware level, we have specific hardware components, security components in the RSL10. So there's an encryption engine, an AES. So you can use that to encrypt data if you want to before you send it over the link. There's some differences I mentioned between the RSL10 and 15 as well. The RSL15 even has secure flash and more encryption, and of course FODA. Both have firmware over the air, so you could update the devices with new inference models while they are deployed over the air. And so all that is also in the development environment, and there's examples for that.
Yeah, that's great. I can't add much to that. Obviously, our focus is on the machine learning piece, and I think the contribution that SensiML makes to this is just the ability to partition where the processing takes place so that it's local. But there are a lot of aspects, and it takes a village to build a solution here, right? So that's why we're partnering with onsemi for some of the security components that are necessary, the firmware over-the-air updates. There's device management solutions that are kind of outside the realm of what we offer, but combined together, I think then these things can be assembled into a solution that can address security quite well.
Yeah, great. Thank you. Just to follow on this, Chris, there is a question from Hitul. I guess it's for you. How effective is acoustic sensing in an industrial environment, especially when there is a noise around? Like, what is your experience with this noisy environmental type of?
Depending on the background noise factors that you're dealing with, again, it's kind of situational, but a lot of it has to do with the signal processing on the front end and making sure that you're getting signal to noise ratio so that the signal inputs that you're getting aren't generating a lot of trouble for you, basically, right? So if you can do conductive or in some cases use vibration sensors, in many cases, that's really the strategy, is that rather than have to do all the processing within the classifier and cover all the negative cases, as much as you can do to sort of increase the signal to noise ratio on the front end. And then we can deal with it as a sort of multi-pronged strategy of the front end pre-processing, and then Also training the model to have the negative cases, which I think is often overlooked, right? People focus in on what they're interested to classify, but it's equally important, as the person asking the question pointed out, that you capture enough negative data that you can be selective in your model.
Yeah. Thank you, Chris. So I think we are running out of time, but there is one more question for Theo on the computer vision side of things and the image sensor. Theo, you mentioned one of the use cases was in a retail environment, kind of looking across the aisle, that type of use case for the items there. In general, computer vision and tinyML vision is one of the areas kind of where this community is developing applications. What kind of image sensor resolution can RSLT10 or RSL15 support in terms of image sensor resolution? And obviously, I assume it's an onsemi kind of sensor type of device.
Yes,
like what can people get in terms of vision applications?
Yeah, there's no limit on the image sensor data. It's just the transport through your Bluetooth link that is then affected, and it will take longer to send that data. If you want to send a complete image frame and then do some other work with that in your cloud, in those applications we have on the edge running something for motion detection or something like that, something very simple as an edge AI, and the video frames are still sent then to the backend for the processing of detecting which products are needed. We have sensors that are 44 megabytes of resolutions versus so all the different resolutions are in our portfolio, and it's not really limited by that. It's really how fast your bandwidth need to be. And so the application, what I pointed out, is that it's something where you take samples of in this case, intelligent retail opposite aisle. It would be maybe several times a day that you do that, and you're not video streaming that.
Just to clarify, Theo, so the image sensor you show is not part of the board; it's kind of a separate sensor, and then you have a Bluetooth connectivity.
It is in that board I showed. The SnapCam board has an image sensor and everything on it, and the battery behind it, and it does the whole thing. It will do motion detection and then send the image frames off into the cloud. I do have to look at what specific resolution of that image sensor is, but as I mentioned, it's not. It's just how long you want to be able to send that data across.
So basically, people can basically buy this board specifically with the image sensor.
Yep.
Yeah. Well, there is I cannot resist not to answer this question from OJ. He's asking, is the future of tinyML on battery-free devices promising?
I think if you use solar or even the mechanical motion for some of those, there's applications for that. Yeah, but Edge AI does require some CPU running and doing things. So the profile of that power profile of such a solution is definitely higher than this getting a temperature sensor and having the sensor programmed to, if you go out of bound and then report that and send that out. That's a different use case.
Okay, great, thank you. I think we ran out of time. Let me just finish with acknowledging our sponsors again. ARM, software and hardware for tinyML. DeepLight, AI to make AI faster, smaller. Edge Impulse, tinyML for developers. EMSA, Edge AI vision sensors. GreenWave Technologies, enabling the next gen of sensor and hearable products to process rich data with energy efficiency. Gravity, software development services for tinyML solutions. HOTG, distributed infrastructure for tinyML applications. Latent AI, they develop adaptive AI for the intelligent edge. Maxim Integrated, enabling edge intelligence with their low-power Cortex M4 devices. Kixo AutoML tool, it's kind of another AutoML company. Qualcomm advancing AI research to make efficient AI ambiguous. Reality AI add advanced sensing to your products with Edge AI tinyML. Renaissance, they have a broad and scalable edge computing portfolio of different silicon products. Seed Studio, the IoT hardware enabler. SensiML doesn't need to be introduced here. Chris did an amazing job here. SynSense from Switzerland, they build sensing and inference hardware for low power neuromorphic computing chips. And Syntiant, they develop end-to-end deep learning solutions for tinyML and Edge AI. Again, next talk will be next Tuesday, as usual, out of Harvard. And thank you all for your participation. And thank you, Chris and Theo, for this great collaborative work and presenting this very interesting and practical use case to the audience and sharing your wisdom and your experience in this space. Thank you again.